Alright, hey guys, we're going to do a video here on how to simplify a radical. And a radical, we all know, is another word for square root. So I'm talking about these things. And we've done a little bit of this in class, probably, if you're watching this video. But we want to know how to simplify radicals to kind of get us ready for geometry next year. So let's kind of dive into it again with a quick review. So we kind of understand that, 2 times 2 is equal to 4. And 3 times 3 is equal to 9, and 4 times 4 is equal to 16. And we refer to 4, 9, and 16 as perfect squares because we know that if we wanted to reverse this process, we would square root 4, or square root 9, or square root 16, and it would be kind of like undoing what I just did. The square root of 4 is 2, the square root of 9 is 3, and the square root of 16 is 4. And this kind of carries on as we get into algebra when we start using variables. So we start saying things like, okay, x times x is x squared. Now x is a number, but I don't know what it is. So all I can say is x times x is x squared, but to undo the x squared, I can take the square root of it. And the square root of x squared is x. And the reason I'm kind of reviewing this is because we're going to kind of be moving ahead into what do we do with numbers that aren't perfect squares. All of these numbers are perfect squares. We have no decimals. We have no issues here. And so maybe to kind of help us for our notes, something that we could write down is why don't we make a chart of what a perfect square is versus a non-perfect square. So perfect squares versus non-perfect squares. Maybe make a T-chart in your notes. And here's kind of what you need to know. The easy way to remember is that perfect squares always come out as nice whole numbers. There's no decimals. So always whole numbers. And non-perfect squares are the ones that you get a decimal. So you usually need a calculator. Need a calculator. Because they don't turn out very pretty. So to like put maybe an example or something in our table here. An example of a perfect square could be something real simple, like the square root of 64. What's the square root of 64? Yeah, it's 8. 8 times 8 is 64. It's a perfect square. An example of a non-perfect square would be something like the square root of 12. Oh, 16. I just wrote 16. I didn't mean 16. I meant the square root of 12. The square root of 12 is not a perfect square. If you try and think of two numbers that multiply to 12 that are the same, 3 times 3 is 9, 4 times 4 is 16. The perfect square is somewhere in between. It doesn't exist. There's a number in between there. So that's usually when we say, okay, we need a calculator. Let's figure out the square root of 12 on a calculator. Well, okay, I'm going to use my square root button down here. And I'm going to put 12 in. And the square root of 12 is, error. Let's do that. The square root of 12 is 3.46. Keeps on going. 4, 1, blah, 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 blah. So about 3.46. So I'm going to use that about kind of wiggly equal sign. It's about 3.46. It's an ongoing decimal here. That's a non-perfect square, and there's a whole lot of non-perfect squares in our world. And there's going to be non-perfect squares in terms of algebra too, with x's and y's. And we're going to look today at how can we simplify a non-perfect square, because it is possible to simplify it down, and that's what we're going to look at. So I think that's what we'll title our next section here. How do I simplify a radical? What can I do? And why don't we start with that square root of 12? So we're going to write example. And why don't we talk about that non-perfect number that we just had? The square root of 12 we just established is totally a decimal, but we could simplify it down. And here's how I'm going to simplify it down. I know 12 is the same as 4 times 3. I'm going to do a little factor tree down here. It really is. 12 is the same as 4 times 3. So if I think about this, this is really the square root of 4 times 3. Well, what's the square root of 4? That's 2. It's a perfect square. So what I'm going to do is I'm going to square root 4 and turn it into a 2. And I'm going to take 2 out of the radical. But the square root of 3 is not a perfect square. So I'm going to leave square root 3 in the radical. And this is going to be my simplified answer. Technically, the square root of 12 is equal to 2 radical 3, simplified down. Now, here's how I'm going to prove that I'm right, to kind of show that I know what I'm doing. Remember, we did the square root of 12 on our calculator, and we said it was about equal to 3.46. Remember that? So I'm going to write it down. Radical 12 is about equal to 3.46. Well, now on my calculator, I want to figure out this 2 radical 3. So I'm going to do 2 times the square root of 3 and kind of double check it here. It should be the same thing. Look, it's 3.4641. It's that exact same decimal. So 2 radical 3 is also about equal to 3.46. They match each other. So essentially what I just did is I just checked my answer. And so when you're asked to simplify a radical, this is the simplified version. Simplified. And it's kind of a strategy we use for when we actually don't have our calculators handy. A lot of times, especially in geometry, we need to simplify a radical because we're not using our calculator. We're calculator free at that point. And so on my calculator, I can totally check and see if I'm right. I can check my decimals, but we want to be able to do this without a calculator. So let's try some other simplifying examples because that's kind of a basic one here. So another example here. How about we say we have the square root of 50? Just pick another number. There are no two numbers that multiply to 50 that would make it a perfect square, but I can break 50 down. I do happen to know in my head that 50 is 10 times 5. I do know that. And I know that 10 is technically 2 times 5. So if I use my factor tree strategy here, 50 is really 2 times 5 times 5. 2 times 5 times 5. And look what happens here. I see 5 times 5. I see something I can pull out of the radical. 5 times 5 is 25. It's a perfect square. So I'm going to pull one of those 5s out, and the only thing left is the 2 inside the radical. 5 radical 2. So my simplified answer is 5 square root 2, and I can leave it like that. So now let's throw some variables in there. Let's say, for the next example, we have the square root of x to the 6th power. Okay, so think about what x to the 6th power means. That means I have x times x times x times x times x times x. 1, 2, 3, 4, 5, 6 x's being multiplied together, all in the square root. Well, every pair of x's makes a perfect square. These are x squareds. X squared, x squared, x squared. And every time there's a perfect square, I can take it out of the radical. I see 1, 2, 3 x's that could come out. I see x to the 3rd power. Now what's left inside the square root after I take all of those out? Nothing. 0. There's nothing left in the square root. So because there's nothing left in the square root, I don't even need it. I'm just going to say the square root of x to the 6 is equal to x to the 3rd. That's my simplified answer. I'm going to leave it just like that. So to make these more complicated, let's try another one. Example. Let's say we had the square root of x to the 5th, y to the 3rd. X to the 5th, y to the 3rd. So breaking that down, that means I have 5 x's being multiplied together. X times x times x times x times x. And I have 3 y's times y times y times y. I'm going to break this into pieces. Anytime there's a pair, it's a perfect square. I see a pair of x's there. I see a pair of x's there. I see a pair of y's. And when I look at this, I'm looking at this saying, okay, well, all the pairs can come out. They can be perfectly squared. So I have x and x, okay, that's x squared. And I have a pair of y, a pair of y's. But left inside the square root, I still have an x and a y. So it's x times y. And I'm left with this as my answer. That's my simplified answer. So let's look at another one. We'll kind of continue to try these. So another example that we could do is we could start mixing variables and numbers inside the square root at the same time. For instance, I could tell you I have the square root of 16x to the fourth, for instance. So now I'm going to look at 16x to the fourth, and I'm going to break that down and say, well, 16 is 4 times 4. X to the fourth is x times x times x times x, and it's all being square rooted. And the idea here is anywhere I have a pair, I can bring it out. So 4 times 4, oh, perfect square, there's a pair. X times x, x times x. Oh, all right, so I have a 4, and I have x and x, that's x squared. And left inside my square root is absolutely nothing. Nothing's left over, so I don't even need my square root. So my answer is 4x squared, simplified. Why don't you try one? Let me give you one. And you can pause the video and see if you got the hang of this yet. So I'm just kind of showing you lots of examples here. So try this one, square root of 24, x squared, y to the fifth. Pause the video and see if you get it right. Okay, so hopefully you're unpausing the video, and we're going to see if you did this correctly. And I want to show you kind of how I'm thinking about this one. 24 is kind of an interesting number. It can break down into 8 times 3, 6 times 4, 12 times 2. There's a lot of choices. So whatever you choose, doesn't actually matter. Let's say you did 6 times 4. I'm going to break that down even farther and say 6 is 2 times 3, and 4 is 2 times 2. And I'm going to write that out in my square root. I have 2 times 3 times 2 times 2. That's my full breakdown. X squared is x times x. And then y to the fifth, that's 5 y's. That's y times y times y times y times y. All inside this big square root. And anytime I have a pair, I have a perfect square. So I see a pair of 2's. I see a pair of x's. I see a couple pairs of y's. So I see 2x, 2x. I see y, so that's y squared. And then left inside the square root, if these are gone, I still have 2 times 3, and I still have this y. So 2 times 3 is 6y, and that makes my answer. 2xy squared 6y. Square root 6y. Okay, so hopefully you got that right when you tried it on your own. Let me show you some other things. Now let's say, for the next example, that there are already some numbers on the outside of the square root. For instance, I had 2 square root 27x to the third. But I wanted to simplify it more. I said, can you simplify this radical for me? So that's kind of what my directions are going to be looking like. Simplify. Simplify this radical. Okay, well, 2's on the outside, so I'm not really going to think about it right now. I'm going to think about the inside. I'm going to think about 27 being 9 times 3, and 9 being 3 times 3. I'm going to break this whole entire radical down. It's really 3 times 3 times 3. 3 times 3 times 3 is 27. And then x to the third power is x times x times x. But it's all in the square root, and then technically there's this 2 out in front that I'm not really thinking about. So looking for pairs, I see a pair of 3's. I see a pair of x's that can come out of the square root. And so I have a 3 here that can come out. I have x that can come out. But I'm still left on the inside with a 3 and an x on the inside. But then after doing all that work, don't forget there was also a 2 on the outside. So this is all times 2. So I just have to remember 2 times 3 is 6. So this is a 6x radical 3x. And now I've simplified my answer. 6x radical 3x. So again, I'm going to give you one. And you pause the video and try and see if you kind of can do this. All right, so for this one, let's say you had -5 square root 20xy squared. Go ahead and pause the video and try that. Okay, so hopefully you've unpaused the video, and we're going to see if you got it right. So 20 is 4 times 5, and 4 is 2 times 2. So I'm going to rewrite this as 2 times 2 times 5. And then xy squared is x times y times y. And it's all in a square root. And then we have a negative 5 on the outside. So I'll just leave the negative 5 here. So I see the 2 times 2, and I see the y times y. And I'm going to take those out as a 2 and a y. And inside the square root, if those are gone, what do we have? We just have the 5 and the x, so 5x. But then there was that negative 5 on the outside, so it's all times negative 5. So negative 5 times 2 is negative 10y, and it's radical 5x. And then that is my simplified answer. And I'm all simplified down. So the idea here is you're just trying to find any perfect squares that are hidden in your square root. If there's a perfect square that you can kind of, I say pull out, we're not really pulling it out, but that you can take the square root of and get out of the radical, then that's what you want to do. You want to break it down as far as you possibly can go. Now there's going to be some weird situations that you're going to run into, and one of them has to do with this. So our last example of these notes today. What if you saw the square root of negative 4? We know the square root of 4 is 2, but this isn't 4, this is negative 4. And so we know if we try to break negative 4 down, 2 times 2 is 4, but one of these would have to be negative, either this one or this one, to make that possible. And really, there's no situation where that could happen inside the square root. And I want to show you something. If you ever try to put this in a calculator, let's try it. Let's do the square root button, and let's put a negative 4 in here and see what happens. Error message. I don't know if you can see that very well, but your calculator kind of freaks out on you and tells you there's an error. There's something wrong. And the reason for this is it's actually impossible to square root a negative number because you can't have negative times a positive. You can't make this work. It's totally impossible. So it takes us into this entire realm of a new world of math called imaginary numbers. I'm not making this up. We have this whole entire world of math about imaginary numbers where we say the square root of a negative number, usually we say negative 1, is imaginary. And we use this letter I to represent imaginary. And there's this whole world of math that we could get into about imaginary numbers. It's pretty strange stuff. It's not something we're going to do in Algebra 1. But later on in Algebra 2 and pre-calculus, you're going to learn all about the world of imaginary numbers. So it's kind of interesting. My math geeky side gets kind of excited about it. The reality side of me says probably not something we're going to use very often. Definitely not in algebra or geometry. So here's the thing you need to know. If you run into the square root of any kind of negative number, let's say negative 5, for our class, for where we're at, what I want you to do is I just want you to identify that this is not possible, and this takes us into what we call the imaginary number world. So when you see it, you can just write imaginary. There's no possible answer to the square root of negative 5. And like I said, it's really interesting stuff. So big idea at the end of this video is that we want to be able to simplify radicals by pulling out perfect squares, trying to shrink the radical down to the smallest numbers possible. And we're going to practice this a lot in class, and like I said, eventually in geometry, you're going to use this a lot. So I hope this helps, and look for the next video.